Hello students, today I'll be teaching you one of the very important topics in chemistry or the basic things that you need to know while you start learning chemistry. That is about atoms and specifically atomic structures. The modern atomic theory that we are seeing, it started in early 1800s, and the old models they seem to replace by the new models every time. You must have heard of Dalton's atomic model, J.J. Thomson's plum pudding model, Rutherford's atom model. These were all the other theories that were there in the line. And today we will be discussing about one of the most important theory that is proposed by Neil Bohr, and it is called Bohr atom model. It is proposed in the year 1913. So let's straight away go into the Bohr model of atom. What are the postulates? The electrons revolve around the nucleus only in the selected circular paths called orbits. So his first postulate is about orbits, and he said that the electron that is revolving around the nucleus is they can only travel through a particular path, and that path is called orbits. And the peculiarities about these orbits is that they have got definite energy and they are called energy shells or energy levels or quantum levels. So they are also numbered as 1, 2, 3, 4, etc. Or you can say that K, L, M, N is the other designation that we can give. So this is the first postulate that the electrons are revolving around the nucleus only in a selected circular paths called orbits. And the next postulate is, as long as an electron remains in a particular orbit, it does not lose or gain energy. So as long as your electron is in that particular orbit, it is not able to losing energy or gaining any energy. So that means the energy is in that orbit is remaining constant. So therefore, we can say or we can call them as stationary states as well. So this is the second postulate. As long as your electron is in that particular orbit, they are not able to gain or lose energy, and the orbit remains constant. And these orbits are called stationary states. And only those orbits are permitted in which angular momentum of an electron is a whole number multiple of h by 2 pi. This factor is very important. So your orbits are able to move around the nucleus. Your electrons are move around the nucleus in this particular orbits by using this particular angular momentum, that is a whole number multiple of h by 2 pi factor. And you can also say MVR, that the momentum is NH by 2 pi. N can be 1, 2 or 3. So the whole number multiple of H by 2 pi is something that is required for an electron that is revolving around the nucleus. So we can also say that angular momentum of electron in an atom should always be quantized. That is something that is very important. So the angular momentum of an electron in an atom should be quantized. The fourth postulate is, if an electron jumps from one stationary state to another, it will absorb or emit radiation of a definite frequency, and thus giving you a spectral line of that frequency. So your electron is in just imagine it is in the ground state. It is going to the higher energy state and it is able to emit certain radiation, and then it is going into the higher energy states, and they gives a spectral line. And that spectral line depends on certain factors like the initial level and the final level. And the electron which jumped into the upper state, when it is coming back to the lower state, it also radiates same amount of energy in the form of a radiation. So this is his fourth postulate. It is about how you are able to observe spectral lines in a particular atomic spectrum. So this is the postulates by Bohr model. Now let's look into the merits of this atom model. Bohr's atomic model explains stability of an atom on the basis that electrons' energy remain constant in an orbit or shell. So as I told you earlier in the postulates, that the energy in an electron which is revolving around the orbit, revolving around the nucleus is constant. So we can say, or we can explain the stability of an atom with that. The second one is it gives basis to find energy of electron in a particular orbit. If you need to find some energies of a particular orbit, and also you can find the radius of an orbit. These all are possible with the Bohr's atom model. And the third postulate is Bohr's atomic model successfully explained the atomic spectrum of hydrogen atom. So that is something that is very, very important as far as Bohr's model is concerned. So it says that when you are giving a electric discharge is passed through a hydrogen atom, the electron that is in the ground state, it is absorbing some energy and they are jumping into the higher energy states. So as you all know, excited state is not stable. It is unstable. So the electron's tendency is always to come back to the ground state. So when the electron is jumping back to the lower energy state, it is giving out energy. That is in the form of a quantum equal to the difference of energies between the two energy levels, and it appears as a spectral line. So this we already discussed in the postulate session. So that is one of the merits of Bohr model. So he is also proposing an equation where you have E1 and E2 as energies of lower and higher energy level. And if you also have the frequency that is nu, then E2 minus E1 is equal to h nu is the equation. Or you can say nu is equal to E2 minus E1 divided by h. So if you know the energies of two states and if you know the Planck's constant, then you can easily find out the frequency. So these are the merits of Bohr's atom model. So this is a spectral line that we are observing in the case of hydrogen atom. The lines are arising from higher energy states. When they are coming back to the ground state, you are getting these different types of series. Layman is a series where you have transition of electron from higher energy level to the first level. N is equal to 1 is the first level. And it is coming back to the first energy level. We can call it as Layman series. When it is coming to the second, from the higher energy levels, when it is coming to the second energy level, then we can call it as Balmer. When it is coming to the third energy level, we can call it Pascal. And when it is coming to the fourth, we can call it bracket. And when it is 5, we can call it perfect. So these are the different types of emission spectrum that you can observe in the case of hydrogen atom. This is one of the very important applications of Bohr's model. Now, every theory comes with some limitations or some demerits. For the atom model of Bohr, these were the limitations. They were not able to explain the spectra of atoms containing more than one electron. We were discussing about hydrogen. As you know, hydrogen is only having one electron. So for one electron system, his explanation is fine. But what about something that is having more than one electron? Then his atom model has got limitations. Then this model failed to explain the fine spectrum of hydrogen atom. They are also not able to explain the splitting of spectral lines when you have the presence of magnetic field or electric field. Magnetic field, you can call it that phenomenon is called the Zeeman effect. Electric field, it is called a Stark effect. So these effects, when it is present, the splitting happens of the spectral lines. Splitting happens. This was not able to explain by Bohr. And the Bohr's model also failed to explain the shapes of certain molecules. And they were not also in accordance with the dual nature of electron, as de Broglie suggested. There is a dual nature that was not able to explain by Bohr model. And also it violates Heisenberg's uncertainty principle. So that is the limitations. And as we come to the dual nature of this matter and radiation, As I told, just want to tell you what is this dual nature meant by. De Broglie in 1924 proposed that light radiations, all moving particles such as electrons, also should have dual character. So De Broglie suggested that electrons should have dual character, that it should have both wave and particle character. So that is a dual nature. That is what we are talking about. And he also derived a relation that connects wavelength lambda and momentum p. That is this Planck's equation E is equal to h nu. And he combined Planck's equation E is equal to h nu with the Einstein's equation E is equal to mc square. So this is what he did. So he combines these two equations, E is equal to h nu and E is equal to mc square. So we can say that as the left hand side is same, we call h nu is equal to mc square, and nu, we also know that nu is c by lambda. So instead of nu, we can propose c by lambda. So h c by lambda is equal to mc square, or lambda is equal to h by mc by cancelling c. Replacing the velocity of light c, we can also replace the velocity of light c by the velocity of a moving particle v, and the equation turns out to be lambda is equal to h by mv, and as you know, mv is momentum into velocity, that is mass into velocity, that is momentum p. So this is de Broglie wave equation, and the lambda is the wavelength, and the wave associated with this moving particles are called de Broglie waves. So this is about Bohr's model and also something about de Broglie wave equation. So thank you for your patient listening. Thank you.